Hi, I am Vishal. Good morning, one and all. So I am here to explain about robust nonlinear speed control of PM synchronous motor using boundary layer integral sliding motor control technique. So here we start. Permanent magnet synchronous motor drives are being increasingly used in a wide range of applications due to their high power density, large torque to inertia ratio, and high efficiency. This paper deals with the nonlinear speed control of a surface distribution, since the dynamics of the currents are much faster than of the mechanical speed. The speed is considered as a parameter rather than a state variable, and the system equation can approximately linearized by the field orientation. So however, this approximate linearization leads to the lack of torque due to the incomplete current control during the speed transient reduces the control performance in some applications such as industrial robots and machine tools. So here a solution to overcome this problem proposed by DFL is to consider the motor speed as state variable in electricians, so which results in an online on which, which results in an on linear model. Then the nonlinear arc method, called a feedback linearization technique, is applied obtain a linearized and decoupled model, and the linear technique is employed to complete the control design. So the then on linear controller is very sensitive to the speed measurement error, but it can be improved by carefully electing gains in the linear control loops. However, besides the measurement error, the rare parameter variations such as resistance, flux, and the inertia due to the temperature rise and load. So here we can see a model of PMSM. So the machine considered is a surface mounted PMSM, and the nonlinear state equation in the synchronous DQ reference frame can be represented as follows: dx by dt is equals to f of x plus gu. Consider it as first equation, so where x is equals to x1, x2, x3 in the matrix form, and is equals to x1 is equals to id, x2 is equals to iq, x3 is equals to ohm. So here we take u is equals to u1 u2 in matrix form. So here we can say u1 is equals to vd and u2 is equals to vq. So g is equals to 1 by ld 0 0 0 1 by ld 0 in a matrix form. So we can have these are the four equations we are assuming. So now f of x is equals to f1 of x into f2 of x, f3 of x in the linear equation. So minus p, so f1 of x is equals to minus r by ld x1 plus p x1 plus p into lq by ld x2 into x3. f2 of x is equals to minus p ld by lq x1 x3 minus r by lq x2 minus p of 5 by lq into x3. So f3 of x is equals to 3 by 2 p of 5 by j into x2 minus f by j into x3 minus tl by j. So consider it as fifth equation. Now, the nonlinear speed control of PMSM using output linearization in order to avoid any zero dynamics and to get a total input-output linearization, the direct axis current and mechanical speed are chosen as outputs. So, and the assumptions that the load torque is constant. The relationship between the outputs and inputs of the model can be obtained as dI by di d to d square home by di square is equals to b plus a of vd by vd vq. So where b is equals to 3 by 2 1 by j of p into 5 of f1 by f2 minus 2 by 3 2 by 3 f into f3 function f3. A is equals to 1 by ld 0 0 3 by 2 p 5 by l5j. So we take it as vd into vq is equals to a inverse of minus b plus of v1 by v2. As the control laws for the new control inputs, the linear controller employed by Leporol becomes as follows. Where k11 k2 in the 12th equation we can see the equation which we derived. So here where k11 k21 and k22 are the gains, id and ohm are the tracking commands of the direct axis current and mechanical. So here we can see the diagram as a asymptotic load torque observer nonlinear controller. We can see k11 k22 k and k21. It is a block diagram of conventional nonlinear control scheme. So here we can see the equation dc1 by dt plus k11 c1 is equals to 0, d square c2 by dt square plus k21 into dc2 by dt plus k22 c2 is equals to 0. So here we can see the asymptotic load torque observer for the control schemes where the poles employed in where the poles for the designed error dynamics can be chosen by selecting the gains using a binomial standard form. The overall conventional nonlinear speed control system as follows in this employing a rectilinear asymptotic speed trajectory generator in the motor. This paper and information on the acceleration is needed for the state feed. Unknown load torque for the unknown and inaccessible inputs. Observer was studied by Meditech and Ostrater and a observer. For simplicity, the observer is derived under the assumption that time variation of the unknown and inaccessible input is 0. Thus, the inaccessible load torque can be assumed the system for the disturbance torque observer. So here the equation we can see dz by dt is equals to dz plus kew. So y is equals to ohm plus cz. For this system DC are observable. The well-known asymptotic load torque observer can be designed as dz by dt is equals to dz cap plus EW plus Ly of L of y minus cz cap. Take it as 16th equation. We considered c is equals to 1, 0 and w is equals to it. D is equals to minus f by j minus 1 by j 0 0. So the quasi-linearized and decoupled model. So the actual nonlinear input which employs the nonlinear parameter values and measured mechanical speed is expressed Vd Vq. A is equals to A inverse minus B naught plus V1 V2. Did by dt is equals to R naught minus R by LD id minus P LQ IQ. So we are the new control inputs and A0 and B0 are obtained from using the nominal parameter. A quasi-linearized and decoupled model can be obtained by this equation, where the subscript denotes the nominal parameter values. Measured mechanical speed of a motor. Unlike the linearized decoupled model of 9 and 10, there are unwanted nonlinear and the control input gain for the quasi-linearized and model of 18 and 19, which can degrade the control the unwanted nonlinear terms and exactly known but can estimated as or not, and the estimation errors are bounded some known functions and respectively. The boundary layer integral sliding model technique to overcome the drawbacks of the conventional nonlinear scheme has this. The block diagram proposes robust nonlinear control scheme. So we can see the block diagram of robust nonlinear control scheme and the configuration of DSP based experimental system. So PMS we took PMSM. So as the diagram follows, we can see obtain the minimum value for the each term of summing up each term, obtain the maximum value for the maximum value of each term of summing up each, obtain the estimate by calculating the using by calculating average value of minimum and maximum, obtain the estimation error bound by calculating the difference between minimum or maximum value, repeat steps using 20 to obtain the estimate and estimation error bound. So here we can see the graph where they are speed, command speed, and q axis current. So nonlinear speed control of PM synchronous motor, we can see speed control there, it is increasing, and boundary layers of 2 S1 and S2. Thank you so much.